Hey guys, welcome back to my channel. So in last video, I showed you guys two theorems, or actually two properties of uniform convergence sequence. And in this one, I said I will gonna show you another property of the uniform convergence sequence, but this one is about differentiability of the limits of the limit function. So from the previous properties, you might guess the conditions will be that fn is a sequence of differentiable functions, and fn converge to f uniformly, right? And you might guess, well, this is are the only conditions that we need. Then we might get that f is differentiable. The limit function is differentiable, but actually not. You will need another condition which says that fn prime converge to another function g uniformly. So here we actually have two sequences of uniform convergence, right? The first is the sequence of the functions fn itself, and another one is the sequence of the prime the functions fn prime. Okay, so we will get f is differentiable and f prime is equal to g. The proof of this property is quite straightforward. You only need to use the fundamental theorem of calculus and the previous property about the integrability of the sequence of uniform convergence functions. So I already written here. So first of all, we can write fx be a limit of fn x when n approaches infinity, right? Because if fn converges to f uniformly, right? And here we use fundamental theorem of calculus, but we kind of transform it a bit. So we are actually using the second consequence of fundamental theorem of calculus. So the fundamental theorem of calculus actually have two consequences. The first one will be given a continuous function phi. So we given that function phi is continuous if we have a function fx is equal to the integral from a to x of phi t dt, then we will have that fx itself is differentiable, and f prime x will be phi x, right? So this is the fundamental theorem of calculus. The first sequence. Second sequence would be given a differentiable function g, and we know that g prime equal to some functions, say f or phi. Can still use phi. Then we will have that if you want to get the integral from a to b of phi t gt or phi x, doesn't matter, then we will and the consequence of the integral will be fb minus gb minus ga, right? And we're actually using the second sequence, right? So now we are given that f is differentiable, right? And f prime, not f is differentiable. Fn prime is fn is differentiable, right? And fn prime equals to g. So So here actually we are using that well, here we have fn x. We are actually using fn x minus fn a equals to the integral from a to x of f prime t dt. Fn prime. And this is obvious, right? Because fn itself is differentiable, right? So we transform it to be like move fna to the right hand side, and then we get the equation for fnx, which is fna plus the integral from a to x of f prime and fn prime x. Okay, so the first step is that we use fundamental theorem of calculus. And the second step is quite obvious, right? Because you can actually take in the limit of f and a and this part. And it's obvious that f and a is going to be fa, right? Because f and converge uniformly. And for this part, limit n goes to infinity. We're actually using the consequence of the integrability of a uniform convergence sequence. Remember, we can swap the order of the integral and the limit, so we can first compute limit n goes to infinity fn prime x dx or t dt, fn prime t dt, and this will be gt, right? Because fn prime converge to g uniformly. So we take the integral from a to x of gt, and that gives us the answer. And you know that fx now is equal to fa plus the integral from a to x of gt dt, and the right hand side is differentiable, right? This is a constant, and so this goes to 0. And from the fundamental theorem of calculus, this is also differentiable, which is actually the consequence of the second consequence of the theorem, that is f prime equals to g, right? You're taking the derivative of the integral, and it will be f. I'm sorry, it will be g, and the left hand side is f prime, so f prime is equal to g. This is the theorem of the differentiability of a sequence of functions, sequence of uniform convergence functions. Okay, but actually we have another theorem quite similar to this one, but a bit different in the conditions and the consequences, a bit different, which is, well, now we are not assuming that fn converges uniformly to f, the limit function, but we are going to use some conditions to show that fn is actually uniformly converging to some limit function f, and we can also show that the limit function f is differentiable. The theorem says, now let fn be differentiable, right? This is the same with the previous one. And suppose that we have a point x0 in AB, such that fn x0 is convergent. Now fn x0 is a sequence of numbers, right? Because you have already fixed a point x0. It's like here we have some functions. Now we fix a point x0. So we will get some values, and since we're given a sequence of numbers, real numbers actually, we can say that the sequence is convergent, right? And if we're also given a function g such that fn prime uniformly converges to g in AB, then the consequence will be the sequence of function itself, fn, will uniformly converge to f. And second one will be there exists a function, there exists the derivative of the function f prime, and f prime will be gx. And to prove this theorem, we will also use another criteria for uniform convergence, which is Cauchy criterion for uniform convergence. Cauchy criterion says, as given a sequence of functions fn defined on a set A, it will converge uniformly on A if and only if there exists a epsilon larger than 0 such and if and only for any epsilon larger than 0 there will be a capital N such that the difference between any two functions fnx minus fnx and fmx will be smaller than epsilon for any mn larger than capital N. So this is capital N. And for any x in A. And if you remember Cauchy criteria, Cauchy sequence, I think Cauchy sequence is, I think the difference between Cauchy sequence and the convergence sequence are quite subtle, because Cauchy sequence are basically saying that the difference between any two terms after some capital N. So after some point, if this is a sequence of points, after some points, the distance between any two points will be smaller than epsilon. So actually, the distance will be getting smaller and smaller. So any 2 points will be gathering together because their distance will be very small and almost equal to 0, approaching 0. And for a convergence sequence, it's actually pretty similar, because if a sequence of real numbers or some functions are converging to some limit functions or limit point, then that is actually saying these elements in that sequence is going to be closer and closer to some point, to that limit point or limit function, right? But we say a sequence is convergent. We have to also consider the limit point. Is the limit point contained in that set? If it is, then the sequence is convergent. If the limit is outside that set, it is saying that you can converging to that point, but you cannot reach that point. You can't reach it, can't touch it. Then we can't say that the sequence is convergent. But if we're given that the limit point is inside that sequence, is inside that set, then Cauchy is actually the same as a Cauchy sequence is actually the same as a convergence sequence, right? So I think this is the only difference between Cauchy sequence and the convergence sequence. So you can see actually the Cauchy criteria and the definition of uniform convergence actually the same thing. But one is something about convergence, but the other one is something about Cauchy. But as I just explained, Cauchy is actually quite equivalent to to convergence. And to be uniform, that is to say, for any x in A, there will be a uniform N, right? So the proof of the Cauchy criterion for uniform convergence and the theorem stated before will be in the next video. But you can try to show yourself, because, well, at least this one is quite straightforward. You can, well, simply use triangle inequality to show the Cauchy criterion for uniform convergence is equivalent, I'm sorry, not equivalent, Cauchy criteria for uniform convergence, which is, well, to show the sufficient and necessary conditions. And the proof of this theorem will be a little bit tricky because you will need to construct another function. Actually, you're going to construct a another sequence of functions, Gn. So a little hint will be you're going to construct a sequence of functions Gn that converge uniformly to G. And also you will construct another function hx. This is not a sequence of functions, it's simply a function that is equal to, fmx minus fnx, like this. You can try yourself, but this one's a bit tricky, but this one is quite straightforward. So I will show you the proof, the complete proof, not actually the rigorous proof, but kind of like the idea and how I construct the proof in the next video. So hope you like it. See you in the next one.